Today, I'm going to talk about deep learning acceleration and some advancement in this area in hardware and software perspective. At first, I will start with some motivation behind deep learning acceleration and why do we need to accelerate the deep learning training or the inference in deep learning models. And then I will talk about two recent works, two of my recent works, the GP and Mercury. And finally, I will conclude this presentation. So some motivation. So DNNs are computation intensive and a single pixel input pixel, so needs 30K to 600K and even more operation in a CNN network. So this computation value is even higher when we train a CNN model. So, and recent deep learning and large language models are also even deeper and have more layers, so need even more computation. So we need to improve the computational efficiency of DNN training using hardware and software support. So that's why we have so many recent works in DNN acceleration, and we also focus on two of them in this presentation. So I will start with work at a GP. In this work, Accelerating DNA Training by Adaptive Gradient Prediction, this work has been published in Macro 2023. So in this paper, we propose other GP technique, which adaptively predicts the gradients of errors and therefore accelerate the training of deep learning models. So first of all, I will talk about some motivations behind this work, and then I will provide more details about the main idea at the GP. Then I will present the implementation, hardware implementation of other GP, and in results section, we will see some interesting results that we got using the other GP technique. And finally, we conclude this paper. So this is a simple example of regular DNN process in a DNN model. So at the first step, we have the forward propagation process. After loading the input to the model, we propagate the calculated activations layer by layer from the first layer to the last layer. Then in the last layer, we calculate the loss and gradients of error. Next, we start the backpropagation process. During the backpropagation, we send the calculated gradients of error from last layer to the first layer. And in each layer, we update the weights based on the gradients of errors. So the backpropagation process is almost 2 times slower than the forward propagation process. And as you have seen here, this process is sequential. So, and then this being sequential will slow down the training speed. So the solution for breaking the sequential execution is gradient prediction. Let's see the same model that we used previously to get the details of gradient prediction technique. So here we have a predictor model. During the forward propagation, after each layer is computed, after the activations of each layer is computed, the activation will be sent to a predictor model. Predictor model will get those activations and based on those activation, it will predict the gradients and then send them back to the layer, to the original model to update the weights based on that. We continue this process for the next layers until reach to the last layer. And in this way, we don't need to wait until to the end to update the weights. And eventually, when we reach to the last layer, we already update all the weights and we can train the model without backpropagation process. And since there is now that the weights are updated, but still we need to train the predictor model because they are randomly initialized at the beginning. So so after forward propagation, the naive ideas in this gradient prediction will calculate the errors and calculate the true gradient and then send those true gradients to the predictor model. Predictor model get these true gradients and then it already has the predicted gradients, and based on that it will train its own weights. And we do the same process for all layers until reach to the first layer and update all the predictors model. You can see here that we have several challenges here, and so one of these challenges is the scalability issue. So since here this method use one predictor per layer that is not scalable. So imagine DNN models that have more than 100 layers. So in this way, we need 100 predictors. The second issue is the number of predictions that needs to be done in per layer can be large, and it can go up to 24 million values in big networks. And also previous works in this area, they try to mimic the biological process, and they don't care about the performance of DNN models, and they usually degrade the accuracy significantly. So here, that's why we come up with other GP2, and we come up with solutions for scalability. The solution is using one predictor for all layers. And for solving the number of prediction, we come up with the tensor reorganization technique that we will see more details about that in next slide. And finally, we use adaptivity to improve the performance while keep the accuracy high. So combining all these solutions together, we propose AdaGP, which is a scalable gradient prediction scheme to improve the performance without hurting the accuracy. So now let's see some more details about the main idea AdaGP. So this is the overview of the AdaGP. At the beginning, we have warm-up phase. During this phase, for a few initial epochs, we train both original model and predictor model based on true gradients. The intuition behind warm-up phase is that at the beginning, both the DNN model and the predictor model are randomly initialized. So, and then using this warm-up phase, we will train the predictor model for a few epochs, and that's why, and we can ramp up its gradient prediction ability. Then we have regular process in AdaGP. We have phase BP, that in phase BP is similar to the warm-up phase, and we train both the original model and predictor models based on true gradient. And however, this phase BP, only lasts for few batches, say just M batches, that we will see exact value for this M in next slide. And we also have another phase, which is phase GP. During the phase GP, the AdaGP start using the predicted gradients from the predictor model to update the original DNN model. So in this way, we completely escape the backpropagation process, and we only use the predicted gradient from predictors. And similar to phase BP, phase GP also lasts for a few epochs. Let's say that just a few batches, just K batch of inputs. So, and AdaGP during the training phase, AdaGP switches between phase BP and phase GP in an efficient heuristic that we will see more details about that. So we switch between phase BP and phase GP during the training to keep the accuracy high and also have some saving, some computation saving that has been resulted from skipping the backpropagation process, which is a very slow process in comparison with the forward propagation process. So this is for simplicity in our hardware implementation. We perform some experiment to fix the value of K and M in our during the training, and we come up with this efficient heuristic here. After the warm-up phase, we set the K-M ratio to 4:1, and we keep this ratio for 4 epochs. Later, we change this ratio to 3:1 for another 4 epochs, and we follow this pattern when we change the ratio to 2:1, and finally, we set this ratio to 1:1 for remaining epochs. So this is the heuristic that we use for AdaGP for training the DNN models. Now let's use the same example and see the details of different steps in AdaGP. During the forward pass in phase BP, we send the output activations from each layer to the predictor model. And as you can see here, we only have one predictor. And the predictor model will predict the gradients of weights. But we don't use these predicted gradients to update the weights. We just keep it for the training of predictor model. So we repeat this process for the next layer until reach to the last layer. And in the last layer, during the phase BP, after finishing the forward pass, we have the backward path. The backward path at the beginning, we calculate the error and the actual gradient, true gradient. After this, we use this true gradient and send them to we use them first of all for updating the weights of the original model. And second of all, we send them to the predictor model. Predictor model get this true gradient. It has the predicted gradient and will update its own weights based on this true gradient. We repeat this process for the next layer until reach to the first layer, and during this process, we update the predictor model. Now, what will happen in phase GP? In phase GP, after calculating, similar to phase BP, after calculating the output activation, we pass them to the predictor model. The predictor model will predict the gradient and will send them back to the original model to use those predicted gradients to update the weights. We repeat this process for the next layers. We do the predicted gradient, we calculate the predicted gradients and send them back to the original model to update the weights. We repeat this process for next layers until reach to the last layer. And when we reach here, we don't need to do back propagation and we don't need to calculate the actual gradient, and we skip this process. We result some training speed up for us. So what are the problems in tensor reorganization? For some layers, we need to predict large number of gradients from a small number of activations. So let's take a look at one example. So this is an example of a layer in VGG network. So in this example, we have a layer which has a 3x3 filters, and it has 256 output channel and 128 input channels. The output activation size is like this, 16 by 256 by 28 by 28. And we have lots of neurons that needs gradient prediction. So all these weights needs to have some gradients we update them based on those gradients. So we need to predict 300K values. So which is a large number of values. And for solving this problem, we come up with tensor reorganization technique. Tensor reorganization help to keep the size of the predictor model compact and also ensure the higher quality for the predicted gradients. So in tensor reorganization method, first we do some process, we do some steps to first of all make the input size to the predictor model small, because we want to keep the size of the predictor model very small to have some saving in our training process. So for doing this, we do some initial steps. First of all, we calculate the average across the batch dimension. In this way, we can consider the effects of all samples in a batch. In our example, for example, here, this will output a tensor with size 256 by 28 by 20. Then, considering that each layer's filter have a unique impact on output gradient, we can treat the output channel as the batch size for the input of the predictor model. So in our example here, we will have this input that has 256 samples, and each sample only has 28 by 28 size. So now that we have an input with a reasonable size, next we pass this input to the predictor model to do the gradient prediction. This model has a couple of pooling layer, a small convolution layer with a fully connected layer to be able to apply it on top of all input size. The predictor model then will predict the gradients with shape. For example, here, since the inputs are 128 by 3 by 3, so for each input, it will output one vector 128 by 3 by 3, and will totally result in output which has the same shape as the weights. Now, finally, by doing one reshape on this result, we will have the predicted gradient that we can be use them for updating the weights of the original model. Now, to better realize that what will happen during the training of a DNN model by using AdaGP technique, let's see the timeline of the baseline model and also AdaGP technique. This slide shows an example of a simple DNN model with 4 layers. Here we only have one device or one processor. So for simplicity of explanation, we only have one processor. Also, we suppose delay of backward propagation is almost twice the delay of forward propagation in each layer. In the baseline design, during the forward propagation process, we start from first layer and calculate the activation and go to the next layer until the last layer. Then we calculate the amount of error and loss and send the gradients of weight in each layer from the last layer to first layer and update the weights based on the calculated gradient. So this is the timeline of the baseline design. Now, let's see the timeline of AdaGP in phase BP to find the differences between the AdaGP and the baseline. During the forward propagation, similar to baseline approach, we calculate the activations of DNN model. However, here we have an extra delay, which is related to the predictor model for predicting the gradients of weights. We do this process for all layers till reach to the last layer. And then in this layer, after error and through gradient calculation, we do the backpropagation process, which again has an extra delay related to updating the weights of predictor model. So we repeat the same process for all layers till first layer. And during this process, we update the weights of both original model and predictor model. So as you can see here in phase BP, we don't have any time saving, so any computation saving, because we also have some extra computation, but the major part of saving happens in phase GP. During the phase GP, similar to phase BP, we have an extra delay in the forward propagation process, which is related to the predictor model. We repeat this process for all layers till reach to the last layer. In the last layer, unlike in the phase BP, we don't do the actual gradient calculation and we skip the backpropagation process. So in this way, after finishing the process of the last layer, we can instantly start the operation of next batch. This skipping the backpropagation process will result in training acceleration. So you can find more details in the paper, including how we support various data flows with our technique, including raw stationary data flow, weighted stationary, and input stationary. Also, we talked about how we can apply our method on top of multi-devices pipelining techniques. And we had some speed up over those approaches as well. Now, let's see some implementation details, the hardware implementation of AdaGP technique. This is the overall architecture of AdaGP design. The first part is the general structure of a regular accelerator. It has several processing elements that are connected together, and it has a global buffer and also inputs, weight, and activation ports. For implementing AdaGP, we propose 3 implementation approaches. In first approach, which is the AdaGP Max, we essentially consider some additional processing elements to do the gradient prediction in parallel with original model. Also, we have an extra memory to hold the predictor's weight. This will obviously take more hardware. That's why in the second approach, we come up with another implementation, which is AdaGP efficient. We consider a specific memory for storing the weights of predictor model, but here we reuse the processing elements of baseline accelerator, and this will reduce the overhead of extra processing elements in AdaGP Max. And finally, in the last approach, we have other GP low. In this approach, we don't have any extra hardware for other GP, and we reuse all the existing resources in baseline accelerator. Now, with knowing all the details about other GP, let's see some interesting results that we got from this approach. So for our FPGA implementation, we take 7 FPGA board, and for ASIC implementation, we use Synopsys Design Compiler. Also, we consider the weight stationary data flow as our baseline with 180 processing elements. For accuracy numbers in different DNN models, we use the PyTorch implementation of our idea, and we applied our idea on top of 15 DNN models, and we report accuracy numbers and performance numbers for these DNN models. So this is the result of accuracy comparison with the baseline method for various data sets. So as you can see here, first of all, for CFAR10, other GP improved the accuracy for all models. It's around, on average 0.8%. It increased the accuracy. And then in case of CFAR100, other GP increased the accuracy of 11 out of 13 models. And in the other two cases, we are almost similar to the baseline, and still you can see the accuracy is comparable and even higher. And finally, for the last data set, which is the ImageNet data set, other GP improve accuracy of 3 models, and for the other model, the accuracy remains almost the same and comparable with the baseline design. Now, one of our concerns, if you remember, was the keeping the accuracy high, and these recent works they decrease the accuracy significantly. So other GP keep the accuracy high. Now let's see how much performance, how much acceleration we can get using the other GP for various data sets. So if you see for C410, other GP speed up the training process for this DNN model up to 1.51 times, and on average of this DNN model, 1.46 times. And for CFAR 100, we got 1.52 times speed up, and on average 1.47 times. And for ImageNet, we got up to a speed of up to 1.58 times, and on average we got a speed up of 1.48 times. So you can find more detailed results in the paper, including results for evaluation with transformer models. And also, we also consider some object detection model and show the performance and the speed up for those models as well. So also we provide some details about the predictors accuracy analysis and also multi-device comparative analysis. And you can find more details about the hardware resources that other GP had in different approaches inside of the paper. So now the conclusion. So other GP is the first approach to use adaptive gradient prediction technique for accelerating the DNN training. We use a novel tensor reorganization technique to predict a large number of gradients, and we achieve an average speed of 1.47 times without hurting the accuracy. Now, for DNN acceleration, I want to cover also another work that recently published, which is the Mercury work. So Mercury, or accelerating DNN training by exploiting input similarity. This work has been published in HPCA 2023. And as you can see here, we accelerate the DNN training by exploiting the similarity between inputs and saving those similar computations. So for this work, first of all, I will talk about the motivation behind this work, and then I will provide more details about the main idea of Mercury. Then I will present the implementation details of Mercury. In results section, we will see some interesting results that we got using the Mercury technique, and finally, we conclude this paper. Motivations. So this is an example of an input image. Here we convolve a vector of this input with the related weight to get some partial output. We apply the same process to the next input vector during the convolution process, the convolution of one input with the weights. And as you can see here, this input vector is similar to the previous input vector. And by doing convolution with the same weight, we get the same partial output from this input as well. So we repeat this process for next input vectors. And as you can see, in this example, these input vectors are similar together. As a result, the output of this convolution operation also will be similar. So we can save this if we can save this computation efficiently, we can accelerate the training process. So in a DNN model, we have many input vectors that are similar together. Therefore, their computations also are similar, and we can skip these similar vectors and save their computation. The training process even has more opportunities. So by exploiting these similarities and effectively saving them, we can speed up the training process. So there are two major challenges here. First of all, how can we detect similarity between vectors with minimum hardware and computation overhead? And second, how can we keep the data flow and the architecture of the design the same? So for solving these challenges, we propose Mercury that combines random projection with quantization technique with a specific cache-based structure to exploit input similarity and save their computations. So now let's see the details of main idea Mercury. This is the overview of Mercury technique. It detects the similarity by utilizing a hashing technique and generating the signatures for vectors. Then it uses Mcache, which is a cache-based structure to find similar signatures or vectors. Finally, it reuses the computation result for similar signatures, and it keeps the data flow the same. Now, let's dive into the details of each part. Mercury uses random projection with quantization technique to generate a signature for each input. What is the signature? Signature is a bit sequence. We suppose that when the sequence, we assign one signature to each input vector. So, and we suppose that when the signatures of two input vectors are identical, those two input vectors are similar together, and we can save their computations. So this is a simple example how RPQ works. Let's suppose we have an input X and we totally have three random vectors, which we call them R1, R2, R1, and R3 with different colors. And the size of each random vector is the same as the size of the input X. After doing the multiplication between input and random vector, these are the result of that, and we totally have three results. And next, we do the sign quantization and assign one bit to each result, and it generates a bit sequence that we call this bit sequence signature of the input. So during the second step and the third step, you can see here we just got the sign of the result. If it's negative, we assign 1 to it, and if it's positive, we assign 0 to it, and it finally gives us this signature. Now, if we closely look at this operation, each random vector is like a regular filter in CNN. So for example, here it is similar to a 2 by 2 filter. Also, the multiplication between input and random vector is similar to regular dot product that we have in CNN, convolutional neural network. So RBQ does the convolution operation between inputs and random filters. In this way, this process is similar to regular convolution operation that we can do it with available hardware with the same data flow. So this is a simple example of convolution operation between input and filter. A filter will slide over all the input vectors and will generate some partial result. Now, here we load the random filters similar to regular filters and before them to do the signature generation process. We do the convolution operation And eventually, by doing that, we generate signatures for input vectors. And as you can see here, each input vector has its own signatures that we will use for similarity detection. Next, we use our Mcache structure to find similar signature. Mcache is a regular cache that has a certain number of rows, as you can see here, and each row has a tag part and a data part. At the same time that we put signatures and we populate our Mcache structure, we also fill another array that we call it heat map. This hit, based on the value of signature, we may have miss or hit in our cache. Hit means that the signature of current input vector is similar to the signature of a previous input vector, and we can reuse the previously calculated result and skip the operation of this vector. And having a miss means that we need to do the operations, the convolution operation for this input vector, and we need to put the result, the calculated result, back to the cache for future use. Here, since the cache, the size of our cache is limited, so here we have, other than miss and hit, we have another parameter, another value, which is miss, not no update. We call it MNU. What does this mean? Uh, when a miss happen, but because the cache capacity and limitation in cache, if the cache is already occupied with another vector and we don't have enough space for a new signature, then in this case we can we in this situation we don't put the new signature into the cache, and we don't overwrite the previous values. In other words, our cache structure doesn't have any replacement policy. Instead, we set the heat map to miss no update. It means that in future, when we do the operation for that input vector, we don't need to update the cache with new results. Now, let's see a simple example about how can we use this Mcache structure, and how can we reuse the already computed result for saving some computations. Here, Mcache is already populated and we know similarity between inputs. Next, we have our regular convolution between inputs and filters. In the first input here, based on heat map, since it's a miss, we know that we need to do the computation, and we put the result back into the cache. And we repeat this process for other miss or miss no update cases. But in case of miss no update, we don't put the result back into the cache. And whenever in case of a hit, when we have a hit, we reuse the result stored in the data part of the cache, and we skip the computation for this vector, and we'll go to the next input vector. So as you can realize here, we have some synchronization issue here. What's the issue? Different pieces may compute at different rates. This is because some of these pieces may skip more computations and some of them less. So for solving this issue, we come up with two approaches. One is the synchronous approach. In this approach, faster pieces will wait for the slower pieces before starting the operation of the next input and filter. This approach is easier to implement and has less amount of saving because these faster pieces needs to wait for the slower pieces, and our speed up would be based on the slower pieces. But another approach is the asynchronous approach, that faster pieces don't wait for the slower one, and they start the operation of next filters until a certain point, until there's threshold that we define for it. This approach obviously results in more computation savings, but however, it needs more hardware overhead, such as additional buffers to pass the next filters and inputs and do the computations for them. We can find more details in the paper about each approach. And now inside of the paper, we showed that how can we support other types of layers such as fully connected layer and attention layers. Also, we talked about supporting various data flows such as raw stationary, weighted stationary, and input stationary data flow. Moreover, we talked about an adaptive technique that we use here to increase the performance of the model. That you can find these details inside of the paper. Now, let's see some implementation details about the Mercury architecture. Similar to the baseline accelerator, it has an array of processing elements that are connected together. We consider some hardware for a M-cache structure and also for storing heat map and signature table. We consider some extra hardware. And inside of each P, we have input and weights register and also some buffers to store the inputs in asynchronous approach. We provided more details, more explanation in the paper about different parts of processing element and the type of memory that we use for each of them, that you can find this interesting information inside of the paper. Now let's see some interesting result that we got using this Mercury approach. First of all, for experimental setup, we implemented Mercury in Vertex 7 FPGA board. And for baseline, we use the Iris-style accelerator with 168 processing element. Our M cache has we use the 16-way cache structure with totally 1,024 entries. And we also had the PyTorch implementation for our idea to get the accuracy numbers from 12 different DNN models that you can see here. Now, this slide shows the training speed up and accuracy comparison between Mercury and baseline design. So as you can see here, Mercury speed up the training process on average of 12 different DNN models around 1.97 times, around almost 2 times speed up in training process. And also in the right hand side, you can see that the amount of accuracy loss because of our approach is negligible and less than 0.7% on average of these DNN models. Also, this is the result of a speed up comparison between Mercury and other techniques. Mercury could speed up the training process, as we said, around the 1.97 times. However, the best UCNN configuration result in 1.84 times the speed up, and the unlimited zero pruning approach can get with unlimited zero pruning approach, we can get a 1.8 times speed up, and with unlimited similarity approach, we got the 1.89 times speed up. And you can about this, we provide more details about each of these techniques in the paper and how what is the details about each of them, how can we implement them, and you can find them in the paper. So, and this is another result that related to a specific model, VGD13. In the left-hand side, you can see that in different layers of VGD13, we have significant amount of similarity between input. In some layers, the amount of similarity goes up to 78%. In the right-hand side, we showed the different access type that happens in different layers of VGD13. As you can see here, in the first layers, the amount of miss-no update cases is much more than the last layer. Why it's happening? As you know, during the in a DNN model, at the beginning, the first layers, the input size is much larger than the input size in the last layer. So bigger input size will result with more input vectors, and we have that as a result, we will have more signatures that we need to take care of using our cache structure. And that's why in the initial layers, we will fill the cache much faster. That's why we have more MNU cases. But in the last layer, since the input size is very small, so that's why we don't have that much MNU cases in the last layers. Now, in this paper, in Mercury, we showed that significant number of input vectors are similar, and Mercury provides a novel hardware for similarity detection and utilization. It reuses the existing processing element for similarity detection using the RPQ approach, and it saves computations without changing the data flow. And it speed up training by 1.97 times. Now, in this presentation, we reviewed some recent works in DNN acceleration. More specifically, first we reviewed the details of ADA-GP technique. ADA-GP uses adaptive gradient prediction to speed up the training of DNN models, and it keep the accuracy high and increase the speed up. And it uses the novel tensor reorganization method to predict a large number of gradients, and it achieves an average training speed up of 1.47 times. And second, we saw the details of Mercury approach. Mercury provides a novel hardware for similarity detection, and it reuses the existing processing elements for similarity detection, and it saves computation without changing data flow and speed up the training by 1.97 times.